Welcome to this training series on Apache Accumulo. In 2006, Google published a paper entitled Bigtable, a distributed storage system for structured data, that described the design on which Accumulo is based. Accumulo is an open-source implementation of Google's Bigtable, a distributed key-value store designed to organize trillions of data elements and enable sub-second lookup. Accumulo was created in 2008 by the National Security Agency and became an open-source project supported by the Apache Software Foundation, licensed under the Apache 2.0 license. In this series of videos, we'll discuss the design of Accumulo, how it works, how to write applications for it, and how to administer a cluster of machines running Accumulo. First, I want to describe the motivation for why Accumulo is created, why it is designed the way it is, and the types of applications for which it is best used. Accumulo shares some similarities with databases, but instead of supporting a relational data model, Accumulo provides a simpler data model that allows applications to control data layout and format and reason about the data locality to achieve good application performance. Specifically, Accumulo stores key-value pairs, sorts key-value pairs by the key, and distributes them across a large number of commodity-class servers. As such, Accumulo is a good choice for application developers that want to write applications that serve requests coming from a large number of users to access data from a few kilobytes to multiple petabytes with no change in the application logic. Accumulo also strives to provide these capabilities in a cost-effective way. It is designed to run on commodity-class servers rather than one expensive single server. And it is designed to provide good performance even when most of the data is served from relatively slow-spinning hard disk drives, as opposed to data storage systems that are designed to serve most of the data out of memory. Accumulo does this by keeping applications simple. The ideal Accumulo application is designed to process an individual user request in only a few milliseconds by doing a binary search to find the right server and the right key, performing one disk seek to read the value for a key, followed by an optional sequential read of the next few hundred or so key-value pairs, and returning the key-value pairs to the user. That is the job of Accumulo at the most basic level. And you, as the application designer, have complete control over how the data gets sorted so that your application can access the data it needs quickly and efficiently. This makes Accumulo a better option than some other systems when data sizes far exceed the amount of data that can be stored cost-effectively in memory, and when data access patterns are simple enough to be performed over many independent servers. Beyond the original design of Google's Bigtable, Accumulo has a few additional features that make it especially attractive for certain applications. These include support for applying security labels to each individual key-value pair to allow sensitive data elements to be protected against unauthorized access, the ability to perform parallel reads that makes using a secondary index efficient, and a feature called iterators, which allows applications to push some functionality to Accumulo servers to be performed in parallel rather than by a single client. Accumulo also has a number of features that make running clusters of over 1,000 machines manageable, including automatic recovery from hardware failure, automatic tablet reassignment, and dynamic and unlimited columns. Accumulo is written in the popular Java programming language and is compatible with several other open-source big data projects such as Hadoop MapReduce, Thrift, Zookeeper, Pig, Hive, and Spark. Accumulo has a Thrift proxy that allows clients written in other languages to work with Accumulo as well. In this lesson, we'll discuss the Accumulo data model. At the most basic level, Accumulo stores key-value pairs. These key-value pairs are grouped together into tables. Beyond simply storing them, Accumulo sorts key-value pairs by the key. This allows the value associated with a particular key to be found very quickly by performing a binary search across a set of keys. Clients look up a value by specifying the key, and Accumulo returns the complete key-value pair. Additionally, clients can request the set of key-value pairs that are sorted directly following the key requested. Values in Accumulo consist of an array of bytes. Accumulo doesn't restrict the data in the values in any way. The application is responsible for interpreting the bytes of a value. You can store whatever you want in the value, but Accumulo assumes that it will be able to load several values into memory at once, and so there's a practical limit on the size of values based on the memory of your hardware. Keys in Accumulo consist of multiple components, and these components give application designers some control over how data is handled. We'll talk about the main components of the key first, and then go into more details about each component and how they might be used. Keys consist of three main components: a row ID, a column, and a timestamp. If you're used to working with spreadsheets or with tables in relational databases, the row and column concept will be familiar. A set of key-value pairs that have the same row ID are considered to be in one logical row. Each row can have multiple values, each associated with a column. Row IDs and columns consist of byte arrays. Over time, we may choose to store new versions of a value associated with a particular row and column. The timestamp component allows us to store new versions of a value. We may choose to pay attention to only the newest value for a row and column, or we may choose to retrieve multiple versions if they exist. Timestamps are interpreted as Java long integers and are sorted in descending order. Accumulo sorts keys first by row ID, then by column, then by timestamp. The value is not a part of the key and so does not affect the sort order. Row IDs are first sorted in ascending lexicographical order, such as A to Z. Within one row, columns are sorted in ascending lexicographical order. Finally, within a row and column, multiple versions of values are sorted in descending numerical order. This way, the newest version of a row and column appears first when scanning down a table. Unlike a spreadsheet or many relational database tables, in which a row ID simply tells you that the row is the 100th row, for example, the row ID in Accumulo can contain some useful information. For example, we might choose to identify rows by some unique identifier used in an application, such as an email address. Also, unlike conventional relational database tables or a spreadsheet, rows in Accumulo do not need to have the same set of columns. Each row can have its own set of columns. If there is no value for a particular column in a row, rather than storing a null value under that column, the key-value pair identifying that column simply doesn't exist. This may be the most significant feature of the Accumulo data model, since it allows data that does not conform to a fixed schema, or data whose schema is evolving over time, or data whose schema is sparse, to be stored without imposing processing overhead or a degradation in performance. For example, we may have some social media messages that we're storing in Accumulo. Some of these messages may include hashtags. We may choose to store these hashtags under their own column, with the original message in another column, both under a common row ID. In Accumulo, there's no need to store a null or blank value in rows that don't have a hashtag. There is simply no key-value pair for that column. If we look a bit closer at the Accumulo data model, we find that the column component itself is split into three components. In the original Bigtable paper by Google, the column consisted of two components, the column family and the column qualifier. To those two components, the designers of Accumulo added a third, called the column visibility. The simplest way to begin modeling data in a table is to store column names in the column qualifier component and to leave the column family and column visibility components blank. Accumulo allows these components to be blank. But if we find that our application is frequently accessing some columns together and not others, we may choose to begin to group columns under a common family. Both the column family and column qualifier components consist of byte arrays. If the column family is present, key-value pairs will first be sorted by column family and then by column qualifier. This allows columns in a particular family to be scanned together when reading down a table. If we assign our column families right, this may allow our application to avoid reading data it doesn't need by reading only one or a few column families within a row. Column families can be grouped into something called locality groups as well, which we'll discuss in a later lesson. The column visibility component, which was added to the original Bigtable model, can contain a security label expression that describes what authorization tokens are required in order to read this particular key-value pair. If a user attempts to read a key-value pair, and that user does not present the required set of authorization tokens necessary to satisfy the expression stored in the column visibility, then Accumulo will simply not return this key-value pair to the client. Now we have the complete Accumulo data model. Application designers have a lot of flexibility in terms of how they map application data to this model, and this will determine the order that application data is laid out on disk. We'll discuss considerations and options for mapping data to this model in coming lessons. In this lesson, we'll take a look at Accumulo's architecture. Accumulo is a distributed system that consists of multiple types of processes, each running on one or more machines. In addition, Accumulo depends on some processes from other open source projects for storing data and for managing system configuration. Recall that in the previous lesson, we described the structure of individual key-value pairs. We mentioned that a table in Accumulo consists of a set of key-value pairs. Accumulo will automatically partition tables into tablets when they reach a certain size. These tablets are distributed to individual machines and managed by processes called tablet servers. Tablet servers are responsible for handling user requests for key-value pairs that fall into one of the tablets it is hosting. Accumulo clients communicate directly with tablet servers to read and write data, so the application read and write performance scales close to linearly with the number of tablet server and client processes running. Each tablet server can host up to hundreds or even thousands of tablets. Hosting a tablet involves storing and sorting the data that clients write to each tablet in memory, and occasionally flushing key value pairs from memory to disk, which is called a minor compaction. This frees up memory so a tablet server can start storing more key value pairs. Tablet servers typically store files in HDFS, the Hadoop distributed file system. Files in HDFS can be broken up into relatively large blocks, usually 64 or 128 megabytes or more. Blocks are automatically replicated onto multiple servers. By default, each block is replicated 3 times, with one replica on the server on which the file was created, another on a different server in the same rack, and another block on a server in a different rack. This allows the system to avoid losing data even if an entire rack of machines becomes unavailable, such as when a router for that rack fails. A server running a tablet server is also typically running an HDFS data node process, which allows it to store and access block replicas locally. When a client sends a scan request to a tablet server, the tablet server will read from memory and any files associated with a tablet to create a cohesive sorted view of the data and return it to the client. Over time, the number of files associated with a tablet will grow, and occasionally a tablet server will combine several files into one file in a process called major compaction. Eventually, a tablet will reach a certain configurable size threshold, and the tablet server will decide to split this tablet into 2 tablets. When it does this, it simply has to find a row ID that falls roughly in the middle of the tablet so that the new tablets are as close to uniform in size as possible. No data moves when performing a split. The tablet server simply writes the information about these new tablets to a table called the metadata table. When clients need to find out which tablet contains a particular key value pair, they read the metadata table. They can also find out which server is currently hosting a tablet from the metadata table. All of this work is carried out by the client code library behind the scenes. But how do clients read the metadata table? All clients are configured with the host names where processes called Zookeeper are running. These Zookeeper servers are responsible for storing some configuration information for Accumulo, and all the information they store is replicated synchronously between each server. Typically, there are 3 to 5 of these servers. Zookeeper isn't designed to store large amounts of data because replicating all of the data synchronously between machines becomes harder and harder the more data and machines there are. So Zookeeper is only in charge of keeping track of a small amount of information. One of the things Zookeeper does is to keep track of the location of a tablet called the root tablet. This tablet never splits, and it stores the split points and locations of all the tablets in the metadata table. The metadata table in turn stores the splits and hosting locations of all the other tablets in the system. So a client needs only to be told how to find Zookeeper. From Zookeeper, it will learn the current tablet server hosting the root tablet. From the tablet server hosting the root tablet, it learns the server locations of the metadata tablets that describe the tablets the client is interested in. From the metadata table, the client learns where the tablets that it needs are located, and from there the client can talk to tablet servers holding the tablets it needs directly. Clients aggressively cache this information so they don't need to repeat the lookup process unnecessarily. If a tablet server fails or a tablet is migrated from one server to another, the metadata table will be updated, and clients who ask for a tablet that's no longer hosted by a tablet server can simply reread a small section of the metadata table to learn to which server the tablet has moved. Accumulo's design is described as a shared nothing system. Since each tablet server is responsible for a different partition of the data, and since tablet servers each have their own storage, memory, and processing hardware. Because Accumulo decouples hosting responsibility from storage, which HDFS handles, it is a little more flexible in terms of how it distributes hosting responsibility to tablet servers than systems that require that the data be moved along with the hosting responsibility. This might not seem like a big deal in small clusters, but it becomes more and more important as clusters grow in size and as hardware failures become more common. Since Accumulo is a shared nothing system, it works well with other distributed processing systems like MapReduce and Spark. It is possible to run MapReduce task trackers or Spark executors on the same machine as tablet servers, and have distributed workers communicate directly with local tablet servers to do the bulk processing of data without requiring a lot of network communication. In this video, we're going to show you how to install and configure Accumulo. First, Accumulo requires some prerequisites to run. DNS, or the domain name service, should be configured on all machines in the cluster. Domain names need to resolve to IP addresses and IP addresses back to domain names. Also, it's a good idea to have NTP or the network time protocol running on all machines as well to keep the system time consistent across the cluster. Accumulo is designed to run on major distributions of Linux, and it ships with most major commercial distributions of Apache Hadoop. This is convenient because Accumulo depends on HDFS and Zookeeper having been installed already. In this example, I have HDFS, or the Hadoop Distributed File System 2.6, and Zookeeper 3.4 already installed and running. For details on how to get HDFS and Zookeeper running, see hadoop.apache.org and zookeeper.apache.org. We're going to install Accumulo on one machine, but I'll show you all the steps used to install it on a cluster of machines in a production environment. We'll obtain Accumulo from the accumulo.apache.org website. We'll use wget to download the binary distribution. We can use tar to unpack the tar file. In production, we'll need to install this on each machine that will participate in the cluster. Now we'll need to configure Accumulo. In our installation directory, there's some example files that we can use to jumpstart our configuration according to how much memory we want to dedicate to Accumulo. There's also a script that helps us copy the right example files for our environment. We'll run that now by typing bin bootstrap config.sh. First, it asks us how much memory we want to dedicate to the tablet servers. We'll just use 1 GB for now. Accumulo uses some libraries written in C++ to manage newly created objects in memory directly, rather than relying on the Java garbage collector. By using these libraries, Accumulo will run faster and more reliably. These libraries may need to be built for your environment, so we'll choose to use these native C++ libraries. Next, we get to choose the version of Hadoop we're using. In our case, we're using Hadoop 2. Now we can run the script to build the native libraries. We now have the example configuration files copied into the conf directory. There are two main configuration files, accumulo.env.sh and accumulosite.xml. Accumulo.env.sh is where we tell Accumulo how to find Java, HDFS, and Zookeeper files, as well as to configure overall memory usage for each type of Accumulo process. Accumulosite.xml is used to configure Accumulo's behavior and settings. We'll start with accumulo.env.sh. We need to tell Accumulo the path to Hadoop, the path to Java, and the path to Zookeeper. The memory usage is already set in these example files, but we can change them here if we wish. These are standard JVM configuration directives. Next, we'll configure accumulosite.xml. The only required directives in here are the instance.volume setting and the instance.zookeeper.host setting. Instance.volumes should be set to a comma-separated list of HDFS paths that Accumulo will use to store data. The path should include the host name of the name node, the port number, and the full path to where Accumulo data is stored. By default, this is /accumulo. Instance.zookeeper.host should be set to a comma-separated list of Zookeeper server hostname and port numbers. Also, in production, we'll want to change the instance.secret setting to something else. Other common values to set in here are tserver memory maps max, which is used to increase the amount of memory Accumulo will use to store newly written key-value pairs, tserver cache data size, and tserver cache index size, which control memory dedicated to caching recently read index entries and data blocks, respectively. If you increase any of these, you'll also need to increase the overall memory usage allotted to tablet servers in the accumulo.env.sh file. Finally, we have the section on class paths. This is pre-configured for the way the Apache distribution of Hadoop 2 installs its jar files. If you're using a commercial distribution, you may need to provide alternate locations to these jar files. Next, we'll need to decide how we'll start up and stop Accumulo. Some commercial distributions ship with init.d scripts that will start and stop processes on each machine. Accumulo can be brought up and down via the manager processes that these commercial distributions provide. Outside of a commercial distribution, we can bring up all the processes we need using SSH and some additional configuration files. We'll need to set up the ability to SSH to tablet server machines via SSH without a password. You may have already done this when setting up HDFS, but if not, we'll walk through it. To set up passwordless SSH, we'll need to create a key that we can distribute to the worker nodes. In this case, we're going to leave the passphrase blank. Then we can copy this newly created file to the worker nodes. This will allow our startup scripts to SSH in to worker nodes without us having to type in the password. Once this is done, we'll need to specify the list of worker machines in the conf/slaves file and a list of machines that will run the master process in the conf/masters file. When specifying a machine, we should use the fully qualified domain names rather than IP addresses. Now Accumulo is configured and we're ready to initialize and start it. In this lesson, we'll learn how to initialize, start and stop Accumulo, and do some basic monitoring. In production, we should create a separate Accumulo user that will own Accumulo files and processes. Initialization is a one-time setup step that will prepare a place in HDFS for Accumulo to store data. It will also place initial configuration information into Zookeeper. To perform the initialization, we'll run bin accumulo init. This will ask for an instance name used to identify our Accumulo instance, as well as an initial password for the root user. This initialization only has to be done once and can be done from any machine that has Accumulo installed and is configured properly. Rerunning the initialization script will permanently erase information belonging to an existing instance. In the last video, we mentioned that Accumulo can be started either by a management process that is provided by a commercial Hadoop distribution or via scripts provided with Accumulo. We configured our instance to use the scripts. We can start up Accumulo across our cluster using the bin start all script. This will start up all the processes we need. Once the script is finished, we can verify everything is running by visiting the monitor process in a browser. The monitor is a separate process that listens for updates from the Accumulo master, tablet servers, and the garbage collector process. It can be reached by going to the hostname that we specified for the monitor at port 50,095. The Accumulo monitor shows us information about the health and status of the cluster, as well as some useful performance metrics. What we want to see here is that the master is running, we're connected to Zookeeper, and we have at least one tablet server running. Notice also that there are no unassigned tablets. The monitor has several views that can help us learn the status of particular Accumulo processes. For example, in the master server view, we can see the activities that the master server is carrying out. If any tablet servers have been killed, we can monitor the recovery process as orchestrated by the master from this view. In the tablet servers view, we'll get a list of all the tablet servers participating in the cluster. We also can see the number of hosted tablets per server, as well as the ingest and query activity for that server. The tables view will give us a list of all the tables that currently exist in our cluster. Right now, we just have the 4 default tables that Accumulo creates when we initialize the system. Back on the overview, we can see a few graphs that indicate the activity on the system. This includes the number of ingest entries per second. This is key value pairs per second being written to the system. Another graph for the megabytes per second, as well as the scan entries per second and scan megabytes per second. We also have load average, the number of disk seeks across the cluster, minor compaction and major compaction activity, and how well our index and data cache are working. You'll want to come to the monitor page to verify that Accumulo is healthy before diagnosing any other issues with the system. For example, if the master is down, the monitor will tell us. Similarly, if a tablet server has died, we can find that out by looking at the monitor. Log information will show up here as well. Here we can see there are a few warnings about some configuration changes we might want to make, as well as the loss of a particular tablet server. Log messages will continue to show up on this page. Accumulo will automatically recover from the loss of one or more machines as long as there are some machines still available in the cluster. At times it can be helpful to try to bring back processes that may have failed on servers whose hardware has not failed. To quickly restart processes that may have failed, we can run the start all script. We can verify that processes are back online using the monitor. Now that we've learned a little bit about how to diagnose issues through the monitor, we can talk about how to shut down a cluster. Accumulo clusters can be stopped via the stop all script. This will attempt to have tablet servers write all their information to disk before exiting. In some cases, it can be useful to restart failed tablet servers before attempting to shut down the entire Accumulo cluster. In this lesson, we learned how to initialize, start, stop, and monitor our Accumulo instance. In this video, we'll use the Accumulo shell to carry out some basic tasks. The shell is an interactive process that allows us to manage tables, read and write small amounts of data, and view and change configuration parameters. We'll start up the shell via the Accumulo command with the shell directive. We can specify a user on the command line. Right now we only have one user, the root user, with the password we chose when we initialized Accumulo. Now we're in the shell. We can list commands via help. We can quit via quit. To see a list of tables, we use the tables command. Note that we can use tab to autocomplete commands. Initially, we have 4 tables: Accumulo metadata, which keeps track of all the other tables; Accumulo replication, which is used to replicate data to other Accumulo instances; Accumulo root, which keeps track of the metadata table; and trace, which stores timing information about select Accumulo actions. We typically don't need to use these tables for day-to-day administration, but some of these can be helpful for diagnosing issues. Since we don't have any other users, we can start by creating an additional user and granting it some permissions. We can create a new user with the create user command. We can list the initial permissions for that user using the user permissions command. If we want this user to be able to create tables, we'll need to grant that permission to our new user. Now we can issue commands as our new user, switching using the user command. We can create a new table using the create table command. Note that the shell is now configured to operate on the test table, so table-specific commands by default will apply to the test table. We can insert individual key value pairs into this table using the insert command. We can scan a table via the scan command. We can delete a single key value pair by specifying the row, column family, and column qualifier. Most of the time, data will be written and read by applications, and the shell is used primarily to change table settings or user permissions. Accumulo controls the behavior of the instance and particular tables via configuration directives. In the shell, we can view and edit these directives using the config command. To see a complete list of currently used configuration directives, simply type config. We can specify a filter to only see the types of directives we're interested in. For example, to see the directives that relate to the garbage collector, we can use config-f gc. Or we might be interested in the configuration of a specific table. For that, we use the -t option, followed by the name of the table. If we want to change any of the configuration directives, we can use the -s option to set a new value for a particular directive. For example, to enable the use of a bloom filter when reading from our test table, we can use config-t test-s table.bloom.enabled equals true. We can check to see that our directive is recorded by filtering on the directive name. The original value is shown as well as the overriding value we just provided. To remove an overridden value, we can use the -d option. Many of the configuration directives are managed by Zookeeper and are immediately effective. Some can only be set in configuration files and require a restart to take effect. A complete list of configuration directives and their usage can be found in the official documentation at accumulo.apache.org. Other useful commands include compact, which will consolidate the files used in a table; flush, which will force any entries currently held by tablet servers in memory to be written to disk; and du, which shows the current size of a table on disk. In this lesson, we'll look at how to get started developing applications for Accumulo. Accumulo is written in Java and provides an API for reading and writing data and managing tables. We're assuming that you're familiar with writing Java programs and will focus on the specifics of writing Accumulo applications. To get started developing applications for Accumulo, it's convenient to start with an integrated development environment, or IDE, that supports build tools like Maven. In my case, I'm running the NetBeans IDE. To create a new application built on Accumulo, we simply need to generate a new Maven-based project and add the Accumulo dependency. Now I should have access to the full range of Accumulo client classes that I'll need. If not using an IDE, the Accumulo dependency can be added to the Maven pom.xml file with the following XML snippet. To run a client without Maven, the Accumulo jars listed using the Accumulo class path command need to be on the Java class path. For the remainder of the videos, we'll be using some examples built using a project just like this. The example code can be obtained from GitHub. The example code is also found in your working files folder. We'll check out this code using git clone. We can compile the examples using Maven. This will produce a jar file in the training code/target directory that we can use to execute various classes. Driver class allows us to specify options needed to identify which example class to run, to connect to a running Accumulo instance, and which tables or files the example class expects to work with. In the following videos, I'll type out the full command each time we run an example. This example code uses data from the UN Energy Statistics database, available for download at data.un.org. In these videos, I've downloaded a few of these files and placed them into a data directory. The example code is also found in your Working Files folder. As examples are specific to working with this data, the code should easily generalize to other types and formats. When discussing source code for applications, I'll refer to the example classes used and navigate to the sections that are relevant to the discussion. These classes are intended to illustrate the concepts discussed. In some cases, they can be used as a starting point for an application that you'd like to write on your own. Feel free to use and adapt this code in your own projects, as the code is licensed under the Apache 2.0 open source license. However, this example code will often only illustrate a specific concept and so may not be complete in terms of error handling or other production considerations. In particular, this code doesn't attempt to provide any production quality method of doing authentication. In these examples, we'll be passing in a username and password on the command line, which of course is normally disallowed in production applications. Once we start getting into the specific examples, you'll quickly identify some common patterns that we'll use for connecting to Accumulo and doing basic tasks for reading and writing. In this lesson, we'll look at how to use the Accumulo API to write data to a table. Accumulo is well suited to storing data for highly scalable web applications. It also has some features that make it especially good for storing information from operational data stores for the purpose of analysis. In our examples, we'll use some of the data we obtained from the UN Data website on energy production across the world. These are CSV files containing comma-separated values. No matter where the data is coming from, we have to decide how to map elements of the original data files or data from a web application to the Accumulo data model. How we map this data is the most important decision we have to make because it will affect what types of access patterns our table can support and the performance of each access pattern. We discussed the rationale for this particular table design in the video entitled Table Design in the Performance chapter. For now, we'll start by looking at the Accumulo API for writing data. In the example code in the ingest client.java file, we'll see an example of connecting to Accumulo and writing data to a table. All applications that interact with Accumulo, whether reading or writing, have to connect to Accumulo. The API for connecting to Accumulo involves two objects, an instance object and a connector. The instance object represents a unique instance of Accumulo and is identified by specifying an instance name and a set of zookeeper servers. Once we have an instance object, we can obtain a connector. The connector is used to generate objects that we'll use to read and write data. The connector object will also allow us to manage tables via the table operations method. We use that now just to check for the existence of a table and to create a table if the one we want doesn't exist. We'll talk more about the table API in a future lesson. Next, we use our connector to create a batch writer object. A batch writer allows us to group several writes to a table so that they're sent over the network to tablet servers efficiently. Batch writers are tuned using a batch writer config object, in which we specify the max latency or time to wait and the maximum memory to use before sending off a batch, and the number of threads to use to communicate with tablet servers. We obtain our batch writer via the createBatchWriter method and pass in our table name and the config object. Now we're ready to bring in some external data from a file and write it to our table. In our case, we're reading data from a CSV file, and we'll use the open source CSV parser to do that work for us. Data is written to Accumulo in the form of mutations. A mutation represents a set of changes to make to exactly one row. Accumulo supports making several changes to a row at once, atomically, meaning they are either all made or none of them is made. In the case where one of the changes fails, the row reverts back to its form before the first change in the mutation. To create a mutation object, we specify the row ID of the row we wish to change. Whether or not the row already exists is not important. If a row with a specified row ID does not exist, it will simply be created when the first change is written. In our example, we're using the field in our CSV files that contains a country name as our row ID. This will allow us to look up data by country easily. Next, we specify the columns of this row that we want to change. in this case by calling the put method, which takes a column family, column qualifier, and value. This put method allows us to specify the column family and qualifier as strings, but in fact these can be arbitrary byte arrays. In our example, we're taking the field in our CSV files that contains the type of energy produced and storing an abbreviated version of that as our column family, and the field containing the year information as our column qualifier. For our value, we'll store a string representation of a number that records the number of millions of kilowatt hours produced for this country, energy type, and year. We could add additional changes to this row, but we only have one change we plan to make right now, so we're done setting up this mutation, and we can add it to the batch writer. The batch writer will decide exactly when to ship a set of mutations off to tablet servers and commit them to the table. If we wanted, we could force a mutation to be written by calling the flush method, but not calling flush allows the batch writer to maximize throughput as our configuration constraints allow. We continue to create mutations and add them to the batch writer until we're out of data. Then we close the batch writer. This is important as it allows us to confirm that all the mutations have been written to our table before our client exits. If there's a problem with any of the mutations, we'll see an exception. We'll talk about handling failures in a future lesson. Now that we have our ingest client written, we can run it on several files. Don't forget to build your client code using Maven before running these examples. To run this example, we'll execute our training code jar in write mode and give it the information we need to connect to Accumulo. We'll store our data in a table called UN data. Our client will connect to Accumulo, write the table to the newly created UN data table, parse our CSV file, and write out records. We'll run this on a few more files. These files contain information on several different energy types produced for each country around the world. We can check the output of our client by examining our table in the Accumulo shell. We receive the information from our CSV files as it's been mapped to the Accumulo data model. In this video, we'll learn how to read data from an Accumulo table. To review, we wrote some data from the UN concerning energy production over time by country. We'll look at the access methods that this table design supports and the limits of this design. In our scanClient.java example, we'll see that Accumulo provides a simplified API for reading data using an object called a scanner. Scanners can be configured to look up a given key and return the associated value, and optionally, a number of subsequent key-value pairs. As with our ingest client, we need to connect to Accumulo first by creating an instance object and then obtaining a connector. Once we have the connector, obtaining a scanner object for reading data is a simple matter of specifying the table name and a set of authorizations. We'll cover authorizations in the next chapter on application security. Scanners are typically configured to scan over a specific set of key-value pairs and then fetch those key-value pairs and provide them to our application via a Java iterable interface. This allows scanners to be used in for loops conveniently. If we don't restrict our scanner at all, by default it will provide all the key-value pairs in the table to our application. In our application, we support allowing users to fetch all or a portion of a particular row or a specific column across all rows. If a row ID, in our case country name, has been provided to our application, we tell the scanner to scan over just the key-value pairs of that row. We call this setRange method, which takes a range object. Range objects can take a start key and an end key. We'll use the static method exact, which will create the appropriate start and end keys for our row. This allows our scanner to jump to the data about the country of interest without having to read over any other data. If no row ID has been specified, our scanner will scan the entire table. This allows the user to scan over energy production information for one country or all countries. If the user passes in a column family, we'll restrict our scanner to produce key-value pairs for only that column family. In our case, the column family is used to store the type of energy a country is producing. In addition, the column qualifier stores the name of the year during which the energy was produced. If a user provides a year, we can further restrict the scan to return information for just that year. We store the number of millions of kilowatt hours produced in the value portion of our table. If no column family and qualifier is specified, the scanner will provide all columns for the row or rows returned. This allows users to get information about all energy types in all years, a particular energy type for all years, or a particular energy type for a particular year. With our client written, we can execute several scans. With our scanner configured, we'll iterate over the scanner and print out information about each key value pair the scanner provides. With our client written, we can execute several scans. Here we scan for all the information for one country. Notice that we see all the columns in this one row identified by the row ID Argentina. We can further restrict our scan by specifying a column qualifier and choosing a single energy type. And finally, we can restrict our scan further by specifying a column qualifier, in this case, the name of a year. These scans will continue to be very fast even when we have trillions of key value pairs or petabytes of data stored in our table. Our client also supports scanning over multiple rows and bringing back just the information for a specific column. Here we see a number of countries that produced wind in the year 2005 and the number of millions of kilowatt hours they produced. This type of scan, because it's reading the entire table every time, will take longer and longer as our table grows larger. Finally, if we wanted to find all countries that produce over, say, 200 million kilowatt hours of energy using wind in 1993, we would have to scan the entire table and do our own comparisons on values. This table doesn't support accessing the data that way efficiently. If our application isn't required to allow users to answer those questions, this might be okay. A single Accumulo table can usually efficiently support 2 or 3 access patterns. If more access patterns are required, additional tables can be used to execute these access patterns efficiently. We'll address these in the chapter on intermediate application development. In this lesson, we'll discuss using the API to manage Accumulo's tables. Most of these operations are also available in the Accumulo shell, but it can be convenient to execute some of these functions from an application. In our example code, we have a class called tablecode.java that illustrates some of these methods. The methods for managing tables are available by obtaining a table operations object from a connector. First, a list of existing tables can be obtained via the list method, which returns a sorted list of table names. We can check for the existence of a specific table by calling the exists method, and tables can be created by simply calling the create method and providing a name. It can be convenient to set table properties at creation time by providing a new table configuration object, since it can be somewhat cumbersome to configure more than a few properties via the shell. Tables can be deleted by calling delete and specifying the table name. This will remove the table and all its data. If we don't want to remove the entire table, a range of rows can be deleted from a table using the delete rows method. It can be given a start and end key to remove a specific range of rows, or nulls to remove all the data from a table. This is convenient for emptying a table of its data while preserving the table and all associated configuration information. We briefly mentioned the flush method of the batch writer for ensuring that all pending mutations are written to tablet servers. The newly written key value pairs are then stored in sorted order in the memory of tablet servers until more memory is needed, and the key value pairs are written to disk. In addition, the key value pairs are written to a write-ahead log on disk in the order they arrive. In the case that a tablet server dies, the key value pairs in memory are no longer available, so other tablet servers read the write-ahead log and sort the key value pairs into memory so that they are available to be read again. The table operations object has a flush method that directs tablet servers to write all key value pairs stored in memory for a particular table to disk. Calling flush on a table can be useful before taking it offline or for other operations and can help avoid having to run the recovery process. Another useful method is compact, which instructs tablet servers to consolidate all the files associated with each tablet of the table into a single file. Having just one file per tablet makes reading data easier and faster. In addition, because compaction involves reading files in order to write their data to a new file, the compaction process can be a convenient time to apply table-wide changes to the data, such as aging off old data, purging deleted data from disk, changing compression algorithms, etc. Compactions can be configured to apply to all the data in a table or a specific range of rows. The compact method takes a table name, a start and end row ID, a Boolean for whether or not to flush prior to compaction, and a Boolean for whether or not we want this method call to block until the compaction process is complete. If we specify null for the start and end row, compact will process the entire table. If we don't have this method block, the compaction process will run in the background and our applications can continue or exit. In this lesson, we'll look at the authentication methods Accumulo provides for controlling access to tables. When we first set up Accumulo, By default, we logged in using the root account, which has all the permissions available for creating tables, deleting tables, creating new accounts, etc. As with an operating system, the use of the root account for production applications is discouraged. Rather, we'd prefer to follow the principle of least authority when setting up our application so that we don't have to worry about one application affecting another application's tables, for example. While it's possible to think about accounts as being specific to individual users, more often Accumulo accounts are created to serve a specific application, which in turn may serve multiple users. To create a new account, we'll use the create user command and specify the name of the new account and give it a password. We can list the existing accounts using the users command. By default, this new account has the following privileges, which we can see via the user permissions command with the -u option. A comprehensive list of system permissions can be seen via the system permissions command. Similarly, the list of all table permissions can be seen via the table permissions command. If we don't want this new account to be able to create any tables beyond those we initially specify, we can choose to create the tables for this new account using the root account and then grant permission for our application account to simply use these tables. Here, I'll grant the table.read permission for the UN data table to our application account. We can test out our new account by changing to it in the shell using the user command followed by the name of the account we want to use. We can see this account's permissions via the user permissions command. Let's see what happens if we try to write to this table without the table write permission. We get an authorization failure message. We'll go back to the root account and grant our application permission to write to this table. Now let's verify that we can write to this table and read from it. In some cases, one client may write the data and another client application may read the data, in which case we could create two accounts and only grant write to one and only read to the other. When we run our client code, instead of specifying the root account, we can use our newly created application account to do the work. If the application credentials are somehow compromised, we can change the password for an account via the password command. Or we can choose to remove the account from the system entirely. In this video, we looked at ways for controlling access to specific tables in Accumulo and a few best practices for granting permissions to specific applications. In this video, we'll look at using authorizations to protect sensitive data in Accumulo tables. Accumulo supports labeling individual key value pairs with a column visibility expression that defines what authorization tokens are required to read the associated value. If the requesting user doesn't possess the required authorization tokens, Accumulo will not return the key or value in question. This allows data of varying sensitivity levels to be written to a table, and users of varying access levels to query the same table and only see the data they are authorized to see. In practice, this makes giving access to a wider variety of people easier since users that cannot see all of the data can still be given access to the application, and Accumulo handles preventing those users from seeing data they are not authorized to see. Authorization tokens consist of a string of letters, numbers, underscore, dash, colon, period, and the / characters. Column visibilities consist of tokens combined with Boolean operators and parentheses for making operator precedence clear. In our example, we'll write our same UN data to a table, but this time we'll label each key value pair with a column visibility consisting of a token for the country name, logically ANDed with a token representing the energy type. This will allow us to authorize users to read only certain types of energy readings for certain countries. The code to do this lives in the auth-ingest client.java file. We'll modify the mutations we created in our original ingest client by including column visibilities. Here we're creating a column visibility with a token for energy type, the logical AND operator, and a token for the country. We have a function for removing any characters from the country name that aren't valid for authorization tokens. That's all we need to protect our data. We'll start with a new table and ingest our files. Now, if we try to scan this data, we won't be able to see anything because by default, users have no authorization tokens given to them. We have to explicitly grant authorization tokens. We can use the setAuth command in the Accumulo shell to do this. In practice, application accounts are not typically given the ability to grant themselves additional authorization tokens, as that would allow for an elevation of privilege. Our root account can set authorizations for an application account. We can list the authorizations for a user using the getAuth command. We can use the setAuth command to grant a user a new set of tokens. This allows an application using this account to pass in one or more of the operations in this set. Applications do not have to pass in all the authorizations it possesses, which is useful for seeing data as it may appear to users with less privileged access or allowing users with varying levels of access to use the same application. To read data with these authorizations, we need to also modify our scan client to pass in some of our authorizations. The authScanClient.java file contains example code for doing this. We can specify our authorization tokens by creating an authorizations object and specifying an array of strings representing our tokens. We can also pass in a list of byte arrays that contain UTF-8 encoded authorization tokens. Now we can run our authorizations-enabled client and see some data. In this example, I scanned over the entire table looking at just the wind energy produced for all countries. But because I'm only authorized to read information for Argentina and the United States, this is the only information I see. Note that our scan might define a range of data that is much greater than the data we're authorized to see. Accumulo will scan over this data and filter out anything that the user is not authorized to see. Any data filtered effectively represents wasted work on the part of the server, so application designers should be careful to design tables to avoid an excessive amount of filtering of data. In this video, we'll look at updating data using the Accumulo API. Accumulo never really changes data in its tables. Rather, it writes new versions of values for existing keys. After a newer version of a value is written, any clients that perform a scan after that will see the newer version. By default, clients only read the latest version of a value for a given key, so updates appear to overwrite older values. It's possible to configure Accumulo to keep more than the latest version of a value for a key by changing the options given to the versioning iterator that is configured by default on all tables. We can change these options in the shell. To see the current settings, do config-t in the table name and filter for configuration directives that contain the word verse. This will show us the configuration options for the versioning iterator. To change the number of versions to keep around, we can use the config command, specify the table name, and use the -s option to specify a new setting for this configuration parameter. This will change the number of versions the iterator will keep every place the iterator is used, during scans, minor compactions from memory to disk, and major compactions of multiple files on disk into one file. Clients still have the option to decide how many versions, up to the number that the tablet servers have kept, that they want to see at scan time. The upside of managing updates this way is that the performance of updates is the same as simple writes. Although Accumulo can store more than one version of a value for each key, most applications will want to store the latest value so that updates behave like overwrites. We'll see how writing an update works by first reading a value from an existing table from our previous lessons. Here we see the number of millions of kilowatt hours of wind energy produced in Argentina in 2007. Now we'll update that value by writing a new version of the value for this key. Our code for this is found in the update-delete-client.java file. Code for updates is essentially the same as for simple writes. Here we have a single mutation where we'll put a new value for the same column family and qualifier as before. Our update client takes an option that represents the new value to be stored for this row and column. After writing our update, we can do a read for the same key and verify that the value has changed. Deletes operate somewhat like updates. When a delete is written, it effectively suppresses all earlier versions of a key, so it appears as though the key and value no longer exist. Eventually, tablet servers will remove the older versions suppressed by the delete marker and the delete marker during a major compaction. The API for deletes involves calling the putDelete method on a mutation object and providing the column family and qualifier whose value should be deleted. We'll run our code to delete the value for this key from our table. Now when we try to read this key, we don't see any information. The API also provides methods for deleting a range of rows using the table operations object. See the lesson on the table API for details on this method. Some caveats when doing updates and deletes. First, a mutation should not have more than one change per column. So you can't have a delete and an update or multiple updates for the same column in one mutation. Because updates operate like overwrites, it doesn't make sense to have a delete and an update or multiple updates for the same column anyway. Second, a key includes the column visibility. So if two key value pairs have the same row ID, column family, and column qualifier, but have different column visibilities, that means those two keys are different, and their values do not represent two versions of the value for the same key. Finally, these updates are simple overwrite operations. Update can also imply changes like adding a value to an existing value, either by appending or maybe incrementing a numerical value. These types of updates are harder because they involve reading the existing value instead of ignoring it and writing a new version. These types of updates can be difficult to implement on their own, but Accumulo provides a server-side programming mechanism called iterators that can make these types of updates safe and efficient. We'll cover iterators in a future lesson. In this lesson, we'll look at how to build a table to act as a secondary index and enable a wider range of access patterns over data. Recall from our earlier lesson on writing data to an Accumulo table that we were able to do efficient reads of data for a given country, which we stored under the row ID, and more specific reads by further specifying the energy type and year, which we stored as the column family and qualifier, but that we were unable to find the countries, energy types, and years in which countries produced a specific number of millions of kilowatt hours without doing a full table scan. Table scans are the kiss of death for applications striving to support interactive access for users when data tables grow larger than a trivial amount of data. Even in a distributed database like Accumulo, individual servers may be storing multiple tens of terabytes, which is very unlikely to be scanned in under a second, which is the goal of interactive applications. To support applications that wish to scan over a range of values in our original table, we're going to build a second table to act as an index on our main table that we'll use to make this access pattern very fast, even for large amounts of data. Relational databases make use of secondary indexes, sometimes just called indexes, in order to make specific types of queries execute faster. Our index will have a slightly different setup than our main table, however. Notice that when our access pattern involves looking at information that we've stored in the row ID of a table, the access time is optimal, because we can do a binary search to find the first key of the row we're interested in, and then do a sequential scan to read the information within this row. So the strategy of a secondary index is clear. We need a table in which the information we want to use to define our access pattern is stored in the row ID. We'll take the values from our original table and write them to the row ID of a new, separate table, and we'll also write some information that points us to the original record in our primary table. Our secondary index table is going to have the following structure. The row ID of our index table will store an encoded value of the original table, the column family of our index will store the column family of the original table, and the column qualifier of the index table will store the row ID and column family of the original table. The value of our index will leave blank. We store the row ID of the original table in the column qualifier and not the value of our index table, because you might have multiple occurrences of the same kilowatt hours value for different countries and energy types. Storing the country and energy type information in the key allows us to have multiple index entries with the same kilowatt hours. To create a secondary index, it's useful to write the index entries along with the original data. We'll look at some code for creating a secondary index in the index ingest-client.java file. To create a secondary index, it's useful to write the index entries along with the original data. We'll need to create an additional table to hold our index entries. To keep these tables somewhat in sync, we'll use a multi-table batch writer, which allows us to make writes to the primary table and the index table at the same time. We first create the multi-table batch writer with our desired configuration, and then obtain individual batch writers for each of our tables from the multi-table batch writer. But instead of calling flush and close on individual batch writers, we can call these methods once on our multi-table batch writer, and it will affect pending mutations for both tables. We're also going to make use of another feature of the Accumulo API called lexicoders. To make a long story short, storing any type of object but strings under the row ID of our keys can be problematic if we want to make sure our data is sorted properly. Our index entries will require storing decimal numbers, so we'll use the double lexicoder to ensure that our decimal numbers are sorted in the order we expect. This enables us to scan a range of numerical values easily. We'll write data to our primary table and index at once with our new client. In addition to the original mutation that we used to write to our primary table, we'll write an additional mutation, acting as an index entry. We encode the value of our primary table using the double lexicoder and use that value as the row ID of our mutation for our index table. Then we fill in the column family and qualifier as described previously, and add this mutation to our index writer. When we're finished writing all our data to our primary table and index table, we can call close once on the multi-table batch writer. We can run our new ingest client to create the primary table and its index table. We can use the shell to examine our newly created index table. Here we see a set of index entries, which include the encoded decimal number values, as well as a pointer to the original key of the primary table. In the last video, we talked about writing secondary index tables. In this video, we'll write code to read those secondary indexes to extend the range of access patterns we can support efficiently in our application. Using a secondary index to answer user requests becomes a two-step process. One step involves scanning the index table to identify the keys of the primary table that meet our criteria, and the second step involves scanning multiple keys of the primary table to obtain any other information from the original rows. In cases where we don't need any additional information from the original rows, we can stop at step 1 and return just the information that identifies the original row. Because the second step may involve fetching a relatively large number of individual key value pairs, or short scans of key value pairs, Accumulo provides a client object called the batch scanner to make reading these multiple key value pairs more efficient by reading them in parallel from multiple tablet servers at once. An important caveat when using batch scanners is to remember that while regular scanners return key value pairs in sorted order, batch scanners do not. We have code for scanning a secondary index table in indexScanClient.java file. Let's look at what a client that uses secondary indexing looks like. First, we obtain a scanner for our index table. We use lexicoders again to transform given numerical values into index entries that can be used to scan our index. In our client, we'll allow users to specify a range of millions of kilowatt hours by providing a lower bound and an upper bound. These bounds will define the range object that we pass to our scanner. Next, we transform the results of the index scanner into range objects that we can use to fetch original key value pairs from our primary table. To do this, we use functions that effectively reverse the operations we use to create our index entries from our original key value pairs. The first function retrieves the components of the index entry and recreates the primary key structure. The second function simply gets a range that spans only this key. If we have no results from the index, we simply tell the user so and exit. Now that we have a set of ranges that identify keys of our primary table, we can hand those ranges to the batch scanner, which will fetch the values for them in parallel. As before, we print out the results, this time limiting them to the first 20 results found. When we run our client, we can now specify a range of millions of kilowatt hours that we're interested in, and the client will show us what countries produced energy within that range, along with the energy type and year during which the energy was produced. Unlike a full table scan, this type of access will still be fast as our table grows in size. Also note that columns returned by this batch scanner can be restricted to a specific set of columns, just like the scanner can, and authorization objects are passed to batch scanners as well to restrict access to any sensitive information that a table might contain. This basic technique of storing original data in a primary table under a unique key and writing index entries to a second table generalizes to allow querying any value of any field that the original data may contain. Lexicoders make it easy to generate index entries that sort properly for a variety of value types. For a full list of value types, see the Accumulo Java API documentation for the version of Accumulo you're using. Accumulo's unique support for large rows, dynamic column families, and the batch scanner make using secondary indexing with Accumulo possible. In this lesson, we'll learn how to write applications to handle certain types of hardware failures. Accumulo is designed to run on clusters from 1 to over 1,000 commodity class machines. In large clusters, hardware failures are commonplace, but even in small clusters, we don't want a single hardware failure to cause our application problems, including data loss or data unavailability. Accumulo does a lot of work behind the scenes to avoid data loss and keep data available. We will detect failures, redistribute responsibility for tablets to other servers, and perform any necessary data recovery from write-ahead logs. This means that most of the time, our application doesn't even need to know that a machine has failed. This resilience and response to failure is part of what makes Accumulo so scalable. There are a few scenarios in which our client may see an exception, and we should know how to approach those scenarios. There are basically two types of exceptions that our client might see when attempting to write data. These are permanent errors and transient errors. Each of these are packaged up into an exception object called a mutations rejected exception. The occurrence of a permanent error means that no matter how many times you might try to send a set of mutations to tablet servers, the write will fail. One example of this is when we have a constraint configured on a table and we try to write a mutation that violates that constraint. In this case, we want the mutation to fail and to fail every time because we want the invariant the constraint is enforcing to remain true for our table. These types of permanent errors represent some sort of misunderstanding in the client code that should be fixed. The other type of error is transient, which means that Accumulo tried to write our mutations to tablet servers but could not for some reason that is not necessarily permanent. In the case of a tablet server failing, it's possible for our client to see a transient error during the brief period when the tablets to which it wants to write are unavailable. But by default, batch writers are configured to effectively never time out, and they will simply wait until the recovery process is complete and for those tablets to come back online. This means that our client will typically never see a transient exception because of a single tablet server failure. If for some reason you wish for your application to receive exceptions after a certain period of time during which a batch writer is unable to perform writes, you can set a timeout on the batch writer. We can get verification that all pending mutations have succeeded by calling flush. If we call flush and don't get an exception, we're assured that all our pending writes have made it safely to the write-ahead log of a tablet server, and that even if a tablet server fails, the write will persist. That is true if we're using the default durability setting for our batch writer. In some cases, we may want to use weaker durability guarantees in our client. For example, we may be collecting extra metrics from a web application that aren't critical but are nice to have. In the presence of lots of user activity, we may not want this non-critical information to have a performance impact, and we're okay with losing some of it if a tablet server fails. We can choose to tell our batch writer to use a less stringent durability setting than the default for these writes. The durability setting is configured on the batch writer config object. The levels of durability available are sync, in which all writes must be written to the write-ahead log, for the write-ahead log writes to be flushed from the tablet server to HDFS data nodes, and for the HDFS sync command to have succeeded, guaranteeing that data is on the persistent storage of the HDFS data nodes in order to consider a client write a success. These writes should survive even the loss of power to the entire data center. Flush, in which all writes must be written to the write-ahead log, and for those writes to have been flushed from the tablet server to HDFS data nodes, but not synced. These writes will survive the loss of a single server, but might not survive the simultaneous loss of multiple servers. Log, in which all writes must be written to the write-ahead log, but don't need to be flushed out to HDFS data nodes or synced to disk. These writes will not survive if a tablet server fails soon after the writes are written. And none, in which the writes are not even written to the write-ahead log to be considered a success. These writes will not survive unless a tablet server hosting them has a chance to perform a minor compaction. By default, tables and batch writers use the sync level of durability. It's possible to change the level of durability of a particular table and let batch writers default to the table setting by specifying durability.default in our batch writer configuration. When reading data, Accumulo scanners will block indefinitely in the case of a transient error, such as no tablet servers being online until at least one tablet server can be started. In this video, we'll discuss using the Hadoop MapReduce framework to process data in Accumulo tables. Hadoop MapReduce is a popular framework for doing distributed computation over large amounts of data. Typically, the MapReduce framework is used to process large files in the Hadoop Distributed File System, or HDFS. Because Accumulo is a distributed structured store, MapReduce can also read and write data to and from Accumulo tables in parallel. This allows data in tables to be processed using all of the compute resources in the cluster, so that computations complete much faster than if the data were processed sequentially. To process data from an Accumulo table using MapReduce, we'll use the Accumulo input format. This class tells the MapReduce framework how to connect to Accumulo, which tables to use, and optionally, which rows and columns of the table we want to read. We specify similar arguments to the Accumulo input format as we do for other clients, an instance name, Zookeeper servers, and a username and password. Now that we've defined the input format, our map function will receive one Accumulo key value pair at a time from our table. In this example, we'll aggregate over all the kilowatt hours produced over all time and all countries, broken down by energy type. Our map function then just needs to output the energy type and amount of energy produced as the output key and value respectively. MapReduce jobs that read from Accumulo tables can write the output to several places. We'll write the output to a new Accumulo table using the Accumulo output format. This output format takes connection arguments the same way the input format does. The Accumulo output format can write mutations to more than one table identified by the output key. In our case, we specify a default table name as the destination for our mutations. The output of our map function will be delivered to our reduce function with all the values for each energy type grouped together. Our reduce function just needs to calculate the sum of all these values. We create a mutation object to write the total millions of kilowatt hours produced per each energy type to our output table. The row ID in our output table is the energy type. We have one column family and one value, the total energy production. We pass null as the key to the context.write function to tell the Accumulo output format to write to the default output table and pass in our mutation object. The Accumulo output format will submit this mutation to Accumulo's tablet servers using a batch writer. Classes like this can be packaged up into a jar file and submitted to the Hadoop framework using the mapRed command. In our case, we'll just run this class from our main driver. We can check the output of our job via the Accumulo shell. In our case, we have a very small amount of output, but Accumulo is well suited to receiving large amounts of output from a MapReduce job, over which we want to provide users fast random access via scans. In this video, we'll look at processing data from Accumulo using the Apache Spark framework. Spark is a distributed processing framework similar to MapReduce, except that it provides some additional methods for processing data as part of its API and attempts to keep as much data in memory as possible. Among other things, Spark is especially good for iterative algorithms, such as those used when training machine learning models. In our case, we'll do the same processing we did using MapReduce. Spark can use the same input format classes that Hadoop uses to read data from Accumulo tables. We'll set up the Accumulo input format class the same way we did for Hadoop, but this time we use it to obtain a Spark RDD, which stands for a Resilient Distributed Dataset. RDDs can be cached in memory and processed in parallel on multiple machines. If a machine dies during processing, the data it was processing will be processed on another machine automatically. We use the new API Hadoop RDD method to obtain an RDD of key value pairs. Note that this RDD consists of a set of tuples, each containing one key value pair. We'll use one of Spark's versions of the map function, map to pair, and extract the energy type as the key and kilowatt hours produced as the value. Then we'll call reduce by key to add up all the values associated with each key. Spark doesn't actually perform any processing until it has to, which gives us the ability to do certain types of optimizations. In this example, we're not writing the output to another Accumulo table, but we'll just output the small results to the terminal. The collect function will cause the previously declared functions to be executed on the data from our Accumulo table, and will bring back the results into our client program, where we print them out to the screen. This time we'll submit the Spark job using the Spark submit script. We'll include 4 Accumulo jars in our Spark submit script, so that Spark knows how to talk to Accumulo. We see the output of our job printed to the terminal. Spark has a lot more functions as part of its API and additional libraries for machine learning, graph processing, and SQL operations. But these are the basics for getting data from Accumulo into Spark. In this video, we'll discuss a part of the advanced Accumulo client API called iterators. Iterators allow applications to carry out limited types of operations in an extremely efficient way by executing them on tablet servers. They're called iterators because they take in a sorted set of key value pairs and produce another set of key value pairs following the iterator design pattern. Accumulo uses iterators to perform some of its core functionality. Other iterators can be applied optionally, and developers can write new iterators to apply custom functionality to tables. For example, the kind of summarization we performed using MapReduce and Spark can also be done by iterators running on tablet servers. Accumulo ships with several iterators. There's a set called filtering iterators that can be used to filter out key-value pairs, and another set called combiners that combine several key-value pairs into one key-value pair. In this example, we'll summarize our data by summing over energy produced in all years available for each country and energy type. When we create a table, we can configure it to apply the big decimal summing combiner. The iterator will add up all the values of the key-value pairs that have the same row, column family, and column qualifier. We'll apply this iterator to all columns of our table. We use an iterator setting object to represent the configuration of the iterator. The parameters are the priority of the iterator, the name, and the class that implements the iterator. Iterators are applied in order of priority. An iterator with a priority value of 10 would be applied before one with a priority of 11, for example. We'll use the table operations method of the connector to attach our iterator to our table. Once the table is configured, all we need to do is write mutations with the appropriate keys and values of the right type. Tablet servers will keep all key value pairs we've written and won't apply the iterators until the summarized values are required. Iterators are executed lazily, only when the summarized value is needed by the user. Iterators are applied at 3 times: when scanning a table, when writing mutations from memory to disk in a minor compaction, and when combining multiple files into one in a major compaction. In our client code, we'll write mutations to our table using the name of each country as our row, the energy type as a column family, a blank column qualifier, and the number of millions of kilowatt hours produced encoded to a representation of a big decimal as the value. We'll run our code on our data files and use the shell to examine the output. Because we're using a built-in iterator, tablet servers already have access to the iterator class. But if we're using a custom iterator, we would need to first distribute a jar containing our iterator to the libext folder on all the tablet servers. Our table now contains the summarized information we wrote. Note that although we only see a certain number of entries in this table when scanning, for a short time there may be more entries than this still in the memory of the tablet server or in separate files representing partial summaries. Whenever Accumulo writes this data to disk, it will only write the summary and not the original entries. Because Accumulo iterators allow data to be processed this way, writes into a table with a combining iterator applied have the same performance profile as simple writes. No data needs to be read as data is written. Accumulo simply takes advantage of the fact that multiple values for the same row-column pairs will be sorted next to one another and summarizes the data when it's convenient or when the user asks for the final summary. This makes iterators an extremely efficient way to maintain summarized information over time. In this video, we'll use the Accumulo Thrift proxy as a way to develop applications in languages other than Java. Accumulo's client API is written in Java, and many applications are developed in Java as a result. Theoretically, this API could be used in applications written in any language that compiles to bytecode that can be run on Java's virtual machine, or the JVM, such as Scala or Clojure. The Thrift proxy makes it possible to develop applications in any of the many languages supported by the Apache Thrift project. Apache Thrift is a software framework for scalable cross-language services development, originally developed by Facebook. It allows developers to specify data structures and services in an interface development language, or IDL, which can then be used to generate code for RPC clients and servers in various programming languages. This is great for many web applications, as web developers often need to use languages other than Java to integrate with other web technologies they might want to use, such as a popular Node.js web server written in JavaScript. Accumulo ships with an IDL file that can be used to generate client code for any language Thrift supports. To start the Accumulo Thrift proxy, use the Accumulo command and specify proxy and the proxy properties file to use to configure the proxy. The properties file controls the specifics of the Thrift server that will be started, including the type of serialization to use for data passed to the client and the port number on which it will listen for connections. It also controls which Accumulo instance the Thrift proxy will connect to, as defined by the instance name and Zookeeper servers. Accumulo ships with some client code already generated from the proxy IDL file for C++, Python, and Ruby. If we were using another language, we'd first need to generate the client code for the proxy using the Thrift compiler, which is available from the URL thrift.apache.org. The compiler allows us to generate client code using a command of the form thrift gen, followed by the language ID, and the location of the proxy thrift IDL file. Our client would then reference the newly generated files to work with the proxy. In this case, we're using the pre-generated Python client. Note that when writing an application for the thrift proxy, we don't need the location of the Zookeeper servers or the instance name, just the hostname and port of the proxy and the authentication information. We use this code to start an interactive Python shell. Now that we're connected, we can use the Accumulo API in a way that is similar to the Java clients we've been using. We can list tables and create scanners to read data. To fetch data from a scanner, we call client.nextk and pass in the scanner object, followed by the number of results to fetch, which is a bit different than the Java API. We can then print out the key value pairs we read using Python's iterator idiom. We can also create tables and write data to them. Instead of a mutation object, we'll create a simple Python dictionary consisting of the row ID and a list of column updates to apply. Many applications that are written to interact with the thrift proxy will make use of additional libraries that make working with the proxy a little more natural for each particular programming language. But even though this Python API, for example, is a little different than the Java API, it's still natural or Pythonic enough to get some work done fairly easily. The mileage for other languages may vary. In this lesson, we'll learn about some common table designs that can make working with various types of data easier. Because it is based on Google's Bigtable design, Accumulo, as the research paper that describes Bigtable says, provides clients with a simple data model that supports dynamic control over data layout and format, and allows clients to reason about the locality properties of the data represented in the underlying storage. This responsibility on the part of applications to determine how data is going to be mapped to the Accumulo data model and to reason effectively about the resulting layout means that there are many different ways that tables can be designed, and the right table design for an application may not always be obvious. A good general approach to designing tables is to first consider how data needs to be accessed by an application, and then to leverage the sorted property of Accumulo tables to ensure that data elements that need to be accessed together can be located closely together, either under a common row ID or in separate rows that are sorted together consecutively. This allows applications to satisfy user requests with one or a small number of scans, which ensures good read performance. Secondary to the ways that data will be accessed is to consider how a table design will impact the performance of writes, and how those writes will be distributed across the cluster. To make these ideas more clear, we'll look at two approaches to table designs for different types of data and applications. The first approach we'll discuss is storing data with time-based elements that we would like to read out of Accumulo in time order. Let's suppose that we have an application that is designed to store logging information. This is a pretty common source of data. Each log entry will have a timestamp, and log entries are going to be generated such that the timestamps are always increasing. Let's also suppose that the most common access pattern our application will support is to read out log entries for a particular range of time that users are interested in. Because we know we want to read these log entries sorted in time order, a natural first design is to store the time information as the Accumulo row ID and store any other information in each log entry into the Accumulo value. This makes accessing a range of log entries based on start and end time trivial. We can simply perform a single scan, starting at the start timestamp and ending at the end timestamp. If we did this, however, our application would always write data to the end of our table, meaning to the last tablet in the table, which could be a problem if we want to be able to write more log entries per second than a single tablet server can support. So we can envision a compromise in which we prefix each row with a bucket ID and distribute log entries uniformly across buckets. This allows us to write into multiple points of our table, one for each bucket ID, and within each bucket the data is then sorted in time order. This solves the problem of needing to write data to multiple tablet servers in a cluster, and to read a range of data in time order we now need to perform a scan in each of our buckets. We can implement this in code by randomly selecting a bucket ID within a specified number of buckets and prepending the bucket ID to our row when creating mutations to be written to our table. Note here that we're using the date lexicoder provided by Accumulo to convert date objects into byte arrays that will sort properly as Accumulo rows. When reading from this table, we'll generate a set of bucket IDs and create a range object for each of our buckets, each starting and stopping at a row that is prepended with a bucket ID, again using the date lexicoder. We pass that set of range objects to a batch scanner, which will fetch them from multiple tablet servers in parallel. Batch scanners will return results as they arrive from multiple tablet servers, so we won't have a globally sorted set of results. If a globally sorted set of results is needed, we can just sort our results. This example is a good one for getting a feel for how a design that is optimized for reading might need to be balanced against how that design affects writes. Next, we'll look at a table design that incorporates Accumulo iterators to maintain an efficiently aggregated view of graph data. Graphs are useful for modeling all kinds of real-world phenomena. Graphs consist of a set of nodes or vertices and a set of edges, each of which connects a pair of nodes. Some graphs also include weight information for each edge that can represent anything from the strength of a relationship, as in a social network, to the cost associated with the connection between two nodes in a computer network. Applications that operate on graph data often need to access all of a particular node's neighbors, meaning to look up all the nodes to which a node connects, such as looking up a list of friends of a user of a social networking application. Sometimes applications will need to traverse the graph by looking up the neighbors of a node, followed by the neighbors of those neighbors, and so on. We can choose to organize our graph into an Accumulo table by using the originating node as our row ID, storing edge type information in the column family, if we happen to have multiple types of edges, storing the destination node in the column qualifier, and finally storing the weight information as a value. In our table, we'll go a step further and configure a summing combiner iterator to aggregate multiple weight values written for a particular edge. This allows us to efficiently adjust edge weights as our real-world graph changes over time. With our graph information stored in an Accumulo table this way, looking up all the neighbors of a particular node can be done using a simple scan of the row identified by the source node we're interested in. We've written a function here to help us convert key value pairs back to an edge representation. To find all the neighbors of a set of nodes, we can generate a set of range objects for each node and fetch the neighbors in parallel from multiple tablet servers using a batch scanner. We've really just barely scratched the surface in terms of the number of ways that we might choose to organize data in a table, but this should give you a general idea for the thought process involved. A good table design will allow your application to achieve good performance even if your table consists of trillions or more key value pairs, and allows you to avoid rewriting your application as data sizes grow from a few gigabytes to multiple petabytes. In this lesson, we discussed the considerations for designing tables based on application requirements and the properties of the data to be stored. We looked at a few approaches to some common application scenarios and data types. In this lesson, we'll learn about some additional features that application designers can consider using to further optimize performance. By far the biggest impact to application performance is going to be determined by the overall design of our table. That is to say, the way we've decided to map our application's data to the rows, columns, and values of Accumulo's data model, and therefore how the data ends up being sorted in our table. If the data we want is not organized in a table such that most, if not all, of our data access requests are satisfied by a small number of scans or batch scans, then application performance will suffer. Similarly, if the data we are writing to a table is not well distributed, write performance may not meet application requirements. Provided we've done the work of designing a table to appropriately organize our data according to our application's requirements, there are a few other modifications we can make to a table to make reading and writing data even more efficient. The first of these is Accumulo support for locality groups. Locality groups consist of sets of column families that determine which key value pairs Accumulo will group together when storing them to disk. This is probably best explained using an example. The scenario originally described in Google's Big Table paper is that of storing information about web pages in a table, including the HTML content, information about links contained, and information about how and when the page was accessed. It is reasonable to store all of the information about a web page under a common row, consisting perhaps of the URL of the page. Google actually describes a row consisting of a URL with the components of the URL reversed, so that all of a particular site's web pages are co-located in a contiguous range of rows. Let's say that the content information is stored under a column family called content, and the link and access information is stored under another column family called metadata. This can satisfy the application's primary access pattern, fetching all of a particular web page's information using one scan of a single row, or a single scan of multiple rows if several pages from a common site are required. But an application might have an access pattern that is secondary in importance that consists of scanning over all of just the link information for several pages. When performing a scan like that, it is possible to specify that we only want the information found under the metadata column family for multiple rows, and only that information will be returned to the application. But that will involve needlessly scanning over the content information for each page, which may be much larger than the metadata. Locality groups allow us to group the data under the content and metadata column families into separate sections on disk, so that if we're only reading over column families that lie in one locality group, we don't have to read the data under any other column families. This gives Accumulo a read capability that is similar to what is called columnar storage, or column-oriented storage. Databases have been using columnar storage for a long time to achieve good read efficiency over multiple rows for one or a small number of columns. By default, all column families are stored together in the default locality group. To change this, we simply need to tell our table which column families belong in which locality groups. We can do this by creating a map from the name of a locality group to the set of column families that belong to it. Any column families not mapped to a specific locality group in our mapping will simply be stored in the default locality group. Accumulo doesn't require application designers to specify which locality groups or column families will be used beforehand. If the mapping of column families to locality groups changes, Accumulo will simply start storing newly written information according to the new mapping, and any existing data can be reorganized to conform to the new mapping using compactions. Here we're fetching the mapping of existing locality groups to column families and adding a set of columns to a particular locality group. We use the table operations setLocalityGroups method to tell Accumulo about this new mapping. Accumulo support for dynamically specifying locality groups allows application designers to adjust the table storage layout after a table has been defined to meet primary access requirements as secondary access patterns emerge. Consider using locality groups to improve the performance of any secondary access patterns that your application may be using when scanning a subset of column families across multiple rows. The next optimization feature we'll look at is Bloom filters. Bloom filters in Accumulo allow tablet servers to store a little bit of information in memory about which files on disk might have a particular row, and allows tablet servers to avoid having to open and read files if we know that they don't contain the row a particular scan is interested in. Bloom filters can be enabled for a table by simply setting the configuration directive table bloom enabled to true. Bloom filters are typically most useful when applications need to do a lot of lookups of individual rows. If an application is most often scanning multiple rows, then the performance improvement of Bloom filters will be somewhat diminished. A common access pattern that can benefit from the use of Bloom filters is when fetching a set of individual rows using a batch scanner, as we did when fetching record IDs that matched a query against a secondary index that we described in a previous lesson. Consider enabling Bloom filters when performing these kinds of scans and measure application performance for an improvement. Next, we have block caching. By default, Accumulo caches some information in memory about each file on disk so that it can more quickly identify blocks to read from disk when accessing specific rows. But the blocks themselves are not cached in memory after they've been read. Consider turning on block caching if your application is frequently accessing the same sets of rows. This can be done by setting the table cache block enable property to true. Finally, let's look at manually splitting tables. So far, we've looked at optimizations that can improve read performance. Occasionally, when applications are writing data to particular hotspots in a table, in other words, to a set of rows frequently, consider manually adding splits to a table to better distribute these rows into multiple tablets and therefore multiple tablet servers. For example, we may be writing information about various locations to a table, and we might use rows that consist of first a country name, and then the name of a state, then the name of a city, and finally a zip code. Accumulo is going to automatically split a tablet when the tablet reaches a certain size. but we will likely observe that a disproportionate number of key value pairs are being written to only a few hotspots in our table, corresponding with popular cities such as New York and LA. We might choose to manually split our table so that the tablet containing all the zip codes within New York or LA are split into different tablets. This will allow the Accumulo master to distribute the tablets containing those rows to different tablet servers so that all of the information for New York isn't being handled by just one server. To manually split a table, we just need to tell Accumulo which set of row IDs we would like to split a tablet on using the add splits method. In this lesson, we'll look at monitoring the health and status of an Accumulo cluster. As a distributed system, Accumulo deals with a lot of events that can happen on any of the many machines on which it is running. Many of these are handled automatically by Accumulo, but administrators will still want to know about the failure of individual machines so that they can be replaced or to deal with any particularly troublesome state that a server might be in. In addition, the performance of these individual machines is aggregated to provide applications with highly scalable capabilities. In order to achieve and maintain good application performance, it is important that the workload be well distributed across a cluster. Monitoring individual and aggregate performance is a good way of determining whether the load is well distributed or whether hotspots may exist. Accumulo provides several monitoring mechanisms to administrators and application designers. The first of these is a web application known simply as the Accumulo Monitor. The monitor provides a wide range of useful information about the cluster as a whole, as well as individual tables and tablet servers. The first things that most users are interested in are found on the front page of the monitor. These include the aggregate ingest rate across the cluster, both in terms of key value pairs written per second and in the number of bytes in megabytes, the aggregate read rate in key values per second and megabytes, the average load and number of disk seeks, the number of minor and major compactions, and information about cache hits. Also of primary interest is the table at the top, which will quickly tell us about critical conditions such as the existence of failed tablet servers and the unavailability of any tablets. These issues will be highlighted in red. By clicking on the Tables link on the left, we can see the list of tables, their online or offline status, total number of tablets, the total entries or key value pairs, aggregate ingest rate, and scan rate and compaction activity. This view is useful for seeing how much each individual table is contributing to the aggregate cluster activity. We can click on an individual table to see the list of servers and how many tablets of this table they are hosting. This is useful for seeing how well a particular table's tablets are distributed across servers. Click on the tablet servers link on the left to see the total tablets hosted by each tablet server and overall activity. The running scans, minor compactions, and major compactions have two numbers representing the number of active tasks and the number of tasks queued but not running in parentheses. This view is useful for seeing whether a particular tablet server is somehow overloaded. In some cases, such as when a user has requested the compaction of an entire table, tablet servers may show a high number of queued tasks that they need to work through. The queued tasks in these anomalous cases will eventually go to zero, but a generally persistent number of queued tasks can indicate that more hardware may be required to keep up with the ingest or query rate, or that perhaps some tuning of the ratio of compactions to scans may be in order to better balance resources dedicated to writes versus reads. The relevant tuning parameters in this case can be found by doing a config-f compact in the shell. Administrators may want to experiment with small changes to these numbers in conjunction with monitoring the resulting effects to best tune the cluster for particular workloads. If we want to look at a particular tablet server, we can click on the tablet server host name and see a list of the tablets the server is hosting. This can help us find out if our application is experiencing any hotspots in terms of one tablet being involved in a disproportionate number of scans or writes. If any tablet servers experience a problem, such as running low on memory or failing completely, log messages will be sent to the monitor. This allows us to see important log information from anywhere in the cluster, in addition to any configuration problems that might exist. The monitor can be set to auto-refresh to get a live view. In addition to the monitor, Accumulo processes also write local logs to each server on which they run. These logs can be found either in /var log accumulo, or in some cases /opt accumulo, or other directories depending on how Accumulo was installed by a particular distribution. These log messages can be examined and are automatically rolled like any other. The login configuration is controlled via the generic logger files and log4j properties file in Accumulo's conf directory. Beyond these mechanisms, administrators should be familiar with monitoring the health and status of the underlying HDFS and Zookeeper systems. Accumulo relies on these, so any problems affecting Accumulo that arise from these systems should be dealt with before monitoring Accumulo for problems with Accumulo itself. In this lesson, we looked at ways to monitor the health and status of Accumulo, to hone in on any problems in a cluster, and to determine application performance. In this video, we'll look at operations that can be performed in the shell to manage Accumulo tables. Most, if not all, table configuration is available to applications via Accumulo's API, but often any configuration done by an application is done when initially setting up a table. Additional actions can be applied to existing tables in the Accumulo shell. The Accumulo shell provides a general mechanism for configuring instance-wide and table-specific properties that affect the behavior of the system. This mechanism is the config command. Config can be used to view and alter the configuration of particular properties. Accumulo uses Zookeeper to control most of these properties, but a few can only be changed in Accumulo's configuration files. The config command will explain when a property can only be changed in these files. We can see a list of all the configuration properties by simply running the config command with no options. To see the configuration options for a specific table, the -t option followed by a table name will restrict the list of properties to those that are specific to the table specified. The configuration properties can also be filtered to those that contain a certain string of characters by using the -f command. To change a specific property, we can type config-s followed by the property name and specifying a new value for that property using equals followed by the new value. These changes will be applied immediately and propagated to various processes throughout the cluster via Zookeeper. In addition to the config command, the shell allows us to perform some other tasks on tables. In a previous lesson, we saw how to manually split a table using the Accumulo API. We can get a list of current splits for a table using the getSplits command. In this example, our UN data table consists of a single tablet with no split points. We can split a table manually in the shell using the addSplits command. We can also merge tablets in the shell. This can be useful for reducing the total number of tablets if data has been deleted from some tablets. In this case, it can be useful to merge all of the tablets under a certain size by doing merge -t followed by the table name and the size limit for each tablet. Accumulo automatically manages the compaction process whereby data is flushed from tablet servers to a new file, or when combining multiple files on disk into one file. We can direct tablet servers to flush any key value pairs currently in memory to disk using the flush command. This may result in smaller files than usual. We can manually schedule a compaction for a table via the compact command. There are a lot of options for controlling the parts of a table to which the compact command will apply. This command is probably most often useful for compacting all of the files in a table to ensure that file-specific changes have taken place in all existing files, such as after changing the configuration of locality groups or the compression algorithm used for a table. The delete many and delete rows commands can be used to remove certain rows or all rows from a table. Delete rows allows us to delete all of the metadata for a range of rows or all rows. Delete many can be used to delete more specific data, such as data for a specific column families across a range of rows or all rows. In this lesson, we looked at some table management tasks that can be accomplished via the shell. In this lesson, we'll specifically cover importing and exporting tables. Accumulo stores its data in HDFS, which is responsible for data replication. By default, HDFS makes 3 copies of each file, which obviates the need for traditional backups to avoid data loss caused by single machine failures. However, many continuity of operation plans require making off-site backups in the case of data center catastrophes like a fire or a flood. Accumulo provides a mechanism for exporting tables that can be used to move data off-site or between clusters for other purposes. There are a few operations involved in exporting a table. We'll do all of these in the shell. In the Accumulo shell, the online and offline commands can be used to take a table offline, making it unavailable for scans, and for taking the table back online again. This can be useful when a cluster might be used to store a table for archival purposes. Offline tables are not affected by compactions. We'll use the offline command in a moment. Tables can also be cloned efficiently using the clone table command. This will effectively create a consistent snapshot of a table. We'll clone the UN data table from previous examples here to illustrate. Cloning a table causes the table to be flushed first to ensure that any newly written data in the memory of tablet servers is written to disk. Cloning will not create a copy of the files on disk. All of the files that Accumulo creates in HDFS are immutable. The original table may still refer to those files, but any new data written to the original table will not be written to the clone table. The clone table will have the same configuration as the original table. It's possible to change the configuration at the time the table is cloned. To see how much space on disk a table is using, we can use the du command. Now we can export our table. Tables can be exported and imported to and from other Accumulo instances using the export table and import table commands. To export a table, it must be offline. Now we can run the export table command, specifying the name of our table and a location in HDFS. The backup's UN data directory will contain a file called distcp.txt that is used to export the files for this table to a directory in the same HDFS instance or to another HDFS instance using Hadoop's distcp mechanism, which is short for distributed copy. The backup's UN data directory doesn't actually contain all of the data files used by this table. Distcp requires running a MapReduce job. In this case, we'll perform the distributed copy using the Hadoop command, followed by the distcp directive. We'll specify the file that contains a list of files in HDFS to export for our table. Followed by the destination path to where our data is going to be copied. In this case, we're copying data between 2 directories in the same HDFS instance. The distcp destination can be a different HDFS instance, however, identified by the name node URL used. Once this job is done, the output directory will contain the set of files that comprised our original table. Back in the shell, Accumulo can load and exported tables files from HDFS using the import table command. We'll give our imported table a name, followed by the directory in HDFS that contains our files. Imported tables will be configured the same way as the table we exported. In this lesson, we covered exporting and importing tables to and from HDFS instances. In this video, we'll make changes to the cluster, adding and removing machines. Accumulo is designed to withstand machine failures on a regular basis, especially in larger clusters. So removing and adding machines to and from the cluster is a fairly straightforward process. To add a new tablet server to our cluster, we just need to have Hadoop, Zookeeper, and Accumulo installed on the new machine, and need to have the configuration file set up to point the new tablet server to our cluster. We can configure the new server by entering the URL of the HDFS name node and the list of Zookeeper servers to the properties in the Accumulo site.xml file in Accumulo's conf directory. If the installation of Java, Hadoop, and Zookeeper are identical across the cluster, we should be able to simply copy existing Accumulo env.sh and Accumulo site.xml files to our new tablet server. Once this is done, we can start up the tablet server using Accumulo's tserver command. If Accumulo was installed as part of a Hadoop distribution, we may use init.d scripts to start the tablet server instead. If we are using Accumulo's start and stop scripts, we need to have passwordless SSH set up to this new server, and we'll want to add the hostname of the new tablet server to our slaves file in Accumulo's conf directory. Then we can run the startall.sh and stopall.sh scripts from Accumulo's bin directory. The new tablet server will show up in the Accumulo monitor. The Accumulo master will begin to migrate tablets from existing tablet servers to this new machine immediately, and the new tablet server will begin to respond to read and write requests from clients. Any currently running applications will automatically discover the new tablet server. It's important that the new tablet server have DNS or domain name service entries configured so that clients and Accumulo processes can resolve its hostname and communicate with it properly. If a tablet server fails unexpectedly, the Accumulo master will automatically redistribute the tablets that were hosted by the failed server to remaining healthy tablet servers. Any newly written entries that were in the memory of the failed tablet server will not be saved to regular files, but can be found in write-ahead log files in HDFS. Tablet servers taking over responsibility for a tablet from a failed server will perform a recovery process to read from the write-ahead log and recreate the state of each tablet as it was when the failed tablet server exited. Shutting down tablet servers can be done gracefully to remove them from the cluster and avoid having to perform the recovery process. We can use the bin accumulo admin command to stop a tablet server. This will instruct exiting tablet servers to flush entries that they have in memory to disk before exiting, and remaining tablet servers that take over responsibility for their tablets can load those tablets without going through the recovery process. Tablet servers that we shut down this way will still show up as dead tablet servers in the monitor. But they can be cleared by clicking Clear in the Dead Tablet Server section of the Tablet Servers view. As we mentioned in the lesson on monitoring, if we determine that some tablet servers are overloaded, as indicated by the persistent presence of queued tasks, we can choose to grow the cluster by adding new machines to take over some of the workload. This will ensure that applications have enough resources for user requests to be completed responsively. This capability of an Accumulo cluster to be grown and shrunk dynamically with no changes to configuration files or interruption to running applications makes running a massively scalable cluster much more manageable. In this video, we'll look at setting up replication between two or more Accumulo instances. Each Accumulo instance is highly fault tolerant and uses a variety of techniques to avoid data loss and data unavailability. As such, traditional backups of data in Accumulo tables are both problematic since the size of the data makes copying it non-trivial and in many cases unnecessary. However, there are some circumstances that may require making a complete copy of the data to an offsite system, or perhaps to an archival system. These include anything that can cause an entire data center to go offline, which could range from a sustained power outage to a physical catastrophe such as a flood or a fire, volcano, etc. As of version 1.7, Accumulo includes the ability to continuously replicate data between two or more Accumulo instances in a variety of configurations. Administrators can set up a conventional primary-secondary replication system in which a primary system copies data to a secondary system, but other configurations are possible, including two systems each copying data to the other, or replication between more than two systems, and so on. It is important to note that a single Accumulo instance is considered highly consistent, meaning that after a write to a key value pair in a table succeeds, all subsequent reads of that key will reflect the updated value. But in a replicated system in which clients are allowed to read from either the primary or the secondary, it is possible for a client to read from the secondary after a write to the primary has succeeded, but before that write has been replicated to the secondary. In this window of time, two clients may get different values for the same key, depending on whether they read from the primary or secondary. This may be acceptable or may not, depending on your application's requirements. You may simply choose to allow reads from the secondary system only in the case that the primary system fails, for example, and choose to have the secondary system become the primary system in terms of the destination for all newly written data. This would maintain high consistency in the event of data center failure. In our example, we'll set up a simple case of replicating data from one primary Accumulo system to a secondary. For this example, I have two Accumulo instances set up on two different computers. The primary will be the instance named Training, and the secondary will be Training 2. I'm going to use the names primary and secondary to identify these instances for the purposes of replication. On the primary system, we'll edit the accumulo-site.xml file and add the replication.name property. We'll do this on the secondary system as well. We'll do this before starting Accumulo, so it will pick up this value. Next, we need to tell our primary about each peer to which it will replicate data. In our case, we only have one peer, the secondary system. We'll use the Accumulo shell to do this. First, we can verify that Accumulo knows its replication name via config-f replication name. We'll tell the primary which type of replication system to use and the information to identify the secondary system, which, like all Accumulo instances, in our case consists of an instance name and a set of Zookeeper servers. It's possible to implement other replication systems that can be used to replicate data to a system other than Accumulo. On the secondary system, I've created an account called Replication. I'll use that account to create the replica table, and the replication account will have permission to write to this table. I'll also note the ID of this table. Now I'll tell the primary to authenticate to the secondary using the replication account. In our case, this consists of a username and password. Now we'll need to tell the primary which tables we want to replicate to the secondary. The replication system works by reading Accumulo's write-ahead log files and sending them to peers to be replicated. Write-ahead logs aren't replicated until they reach a certain size and are closed by the tablet server writing to them. For demonstration purposes, we'll generate some dummy data to a test table, so we'll have enough to see the replication system in action. We use the table ID of the replica table so that we can rename the table on the secondary if we want to, without invalidating the configuration on our primary, since the table ID will not change if we rename the table. Our table has an ID of 6, so we'll use that in our configuration on the primary. For the purposes of demonstration, I've overridden the maximum size of a write-ahead log to be lower than the default, so that write-ahead logs will be closed sooner, allowing the replication system to begin replicating them. Now we'll use some of our training code to generate test data to write to our table. If I write data to the primary, I should be able to see it replicated to the secondary after a few seconds. We can monitor the replication process in the Accumulo monitor. The replication link on the left will show us information about the replication process on the primary. The replication system will notice that I've written information to a write-ahead log that should be replicated. It will note this first, but will not replicate the log until it is closed by the tablet server. After a short while, we should be able to see some data in our test replica table on the secondary system. The latency will depend on a few things, including the maximum size that we allow a write-ahead log to reach before closing, and any latency that exists between our two systems because of physical distance and networking, etc. If a write-ahead log remains open for a long time because no new data is being written, the most recently written entries of a table may not be replicated for a long time. You should be careful when using iterators on table replicas, as the replication system does not guarantee that replicated data will be written exactly once. In the previous lessons, we learned about Accumulo's history and design, learned how to develop applications from basic to advanced, looked at using Accumulo's security and performance optimization features, and how to administrate an Accumulo cluster. I hope these lessons have been useful and have given you some skills and ideas for how to use Accumulo in your own projects. There are an impressive variety of software projects built on Accumulo, many of which are also open source. Besides building and possibly contributing your own projects to the open source space, you can also get involved in building Accumulo itself. There are lots of ways to contribute, from simply providing feedback to spreading knowledge, to helping check newly written code, to fixing bugs, and helping refine or create new features. There are lots of resources at the accumulo.apache.org website. You can join the Accumulo mailing list to get up to speed on current efforts, read up on the developer's guide, download new releases and release notes, and check the reference documentation. I wish you the best of luck in working with Accumulo and hope to see or hear from you through the Accumulo community channels.